Well, I wish I could tell you that I was going to help you understand quantum mechanics today, what's really going on. But yeah, if I could, I'd have a Nobel Prize in Physics, quite surely. We're looking at interpretations of quantum theory today. The quotes from some of the famous here, Niels Bohr and Richard Feynman: if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Some people misquote it as if you're not confused by quantum mechanics, then you haven't understood it yet. Feynman, there was a time when the newspaper said that only 12 men understood the theory of relativity, which we're going to study next. I do not believe there was ever such a time. Basically, as soon as it was presented to the world, it just this logic that falls out of experimental observations, right? It's you can do it in high school. We're going to do it, and it's very understandable. On the other hand, I think I can safely say that nobody understands quantum mechanics. And if you think you understood quantum mechanics, sorry, if you think you understand quantum mechanics, then you don't understand quantum mechanics. So yeah, brace yourself, I guess, right? But so we're looking at the ideas of this, like how can a single particle, a photon, go through both slits? Right? Basically, that's the big thing that shocked the world, right? Like how can this possibly make sense? So I'm gonna play some videos. I'm just gonna pause quick to get them set up here. Here we go.
Right. You still haven't answered my question. What were the electrons actually doing between the source and the screen?
It depends on your interpretation, so we don't totally know.
The reason quantum theory seems so counterintuitive is that we have been brought up on classical physics.
Physicists have developed a number of mental pictures of what's happening, but there's no agreement about which one's right.
There's something called the collapse interpretation. The idea is that there's only a wave that passes through the slits, and then the wave, when it arrives at the screen, it collapses, so it's only detected in one of the many possible places it can be detected at the screen.
It seems to behave as a wave in between the source and detector, so it can go around these barriers and go both ways through the slits.
The pilot wave interpretation says that electrons are real particles, like tiny, tiny tennis balls, guided by an unseen wave.
In this case, you can explain why the particle is only detected in one place behind the slits, because there's only one particle.
It's this pilot wave that tells the electron what to do. So the pilot wave mysteriously knows about everything, where everything is in the universe, and it feels whether or not there's a one slit or two slits, or one slit open or the other slit open. And it can somehow tell the electron about this and move it around and get it to go different places.
If wave-guided particles aren't your thing, how about parallel universes? The many worlds interpretation explains the double-slit experiment by saying that parallel universes are being created all the time.
So in quantum mechanics, we have superposition of different states, and the many-world interpretation says that all these different superposition of states are equally real.
The world literally splits into many copies, and so we only see one thing happening, but there are people in another parallel world who see another thing happening.
While some researchers attempt to construct mental images of the quantum world, others think this world can't be pictured. The Copenhagen interpretation says that we should focus only on the results of measurements in quantum experiments.
When an experimenter enters a lab and interacts with a quantum mechanical system, the Copenhagen interpretation says don't ignore that interaction. It's a crucial piece of what's happening.
It's very powerful to restrict yourself to questions about what we can see. It's very powerful to restrict yourself to questions about what we actually do, because that teaches you to think about the experiment in a very honest way, in a way that appeals directly to the experiment itself without invoking extra theoretical ideas.
In the double-slit experiment with electrons or with photons or with buckyballs or anything, the question is what happens between the source, the double-slit, and the screen. John Archibald Wheeler, famous American physicist, said, "This is just a smoky dragon," meaning that we cannot talk about it. We can mathematically describe it, but it is impossible to make a picture.
I think none of these philosophical discussions bear fruit. The only thing that bears fruit are the calculations.
There's no consensus about which interpretation is right, but they all predict the same results for all experiments.
We really do know what's going on at the subatomic level. We have a complete and accurate mathematical description of what happens.
That mathematical description is something everyone agrees on. It allows us to make incredibly accurate predictions, and that's very useful.
Something that people didn't anticipate is that if you have a weird version of reality.
All right, so, yeah. So, as you can see, there's no real explanation of this, although there's many interpretations, all these Copenhagen, many worlds, waveguide, pilot wave, and so on. They, all give the same mathematical predictions, so there's no way to test them. Really are the interpretations, is it really just philosophy, not physics or not science? They just give another way of thinking about what's really happening or explaining it. But the powerful mathematical equations work, right? Perfect, they agree perfectly with experiments over the last 80 years now or so, but none actually explain anything, right? So just to summarize some of them and give a little bit of extra information, the pilot wave, the idea of electrons, photons, buckyballs, these are really particles, but they're guided by a wave. And then Schrodinger's equations, really are those waves, the mathematical equations of those waves. Waves can interact with both slits, and so the particles can be guided accordingly, right? There's a neat video here that I'm going to play about is this what quantum mechanics really looks like, and it's really to do with the pilot wave, but it's a weird physical reality that you can play with basically and look at it with your own eyes rather than being mysterious quantum world that you can't, right? So just one sec here.
Check this out. I'm using this speaker to vibrate a petri dish containing silicon oil. Now if I take this toothpick and I make a little droplet on the surface, the droplet will stay there, hovering above the surface. The droplet is actually bouncing, and it'll keep bouncing for a very long time. Now the reason for this is there's a little layer of air between the droplet and the surface, and the droplet's bouncing so rapidly that that layer never shrinks to about 100 nanometers, which is what it would take for the droplet to recombine with the oil. Now every time the droplet lands on the surface, it creates a wave. But this is a special type of wave, driven by the vibration of the oil bath. It is a standing wave, meaning that it's not traveling out, it's just oscillating up and down. So the droplet makes the wave, and then it interacts with that wave on its next bounce. If the drop lands on one side of the wave, it is pushed forwards. And as long as the bounce of the droplet remains synchronized with the wave, it'll keep landing on the front side of the wave and getting pushed farther forwards. Droplets like these are known as walkers. The bouncing oil drops have been known about since the 1970s, but only recently has it been discovered that you can use these little droplets to replicate many of the strange phenomena of quantum mechanics. Now obviously this is not a quantum system. The droplets are about 1 millimeter in diameter, but you can think of the droplets like quantum particles, say electrons. One experiment that captures the key features of quantum mechanics is the double slit experiment. If you send a beam of electrons at 2 narrow slits, well, the electrons, rather than behaving like particles and ending up in 2 clumps behind the slits, they produce an interference pattern, even when you send each electron through one at a time. With walking droplets, the pilot wave goes through both slits, interfering with itself, while the droplet only goes through one slit. The droplet doesn't move in a straight line, though. It's deflected by its interaction with the wave. The resulting distribution of where the droplets end up looks very similar to quantum double-slit interference patterns. Or take tunneling. In quantum mechanics, it's possible for a particle to get through a barrier that it wouldn't classically have enough energy to get over. This has been demonstrated with walkers by creating a shallow barrier under the surface of the oil. Usually the barrier reflects the pilot wave and its bouncing droplet, but in rare cases the droplet does cross the boundary. And the probability of the droplet crossing the barrier decreases exponentially with the increasing width of the barrier, just as in quantum tunneling. Perhaps the most surprising thing about these walkers is they exhibit quantization, just like electrons bound to atoms. Here the walker is confined to a circular corral. The droplet seems to move around randomly as it interacts with its pilot wave. The complex interaction between the droplet and the wave leads to chaotic motion of the droplet. But over time, a pattern builds up. This is the probability density of finding the droplet at any point within the corral, and it looks very similar to the probability density of electrons confined in a quantum corral. All of these similarities are no coincidence. The walking droplets actually create a remarkable physical realization of a theory proposed by de Broglie nearly 100 years ago in the early days of quantum mechanics. He postulated that all particles have a wave that accompanies them and guides their motion, and that wave is actually created by tiny oscillations of the particle. Now, this pilot wave theory was marginalized when the standard Copenhagen interpretation became widely adopted. The Copenhagen interpretation excludes anything that cannot be directly observed, and it says everything that can be known about a particle is contained in its so-called wave function. But adopting this view forces you to give up on some common sense notions, like the idea that particles have a definite position and momentum even when they're not being measured. And it also meant that the universe was no longer deterministic. Randomness is built into standard quantum mechanics. For example, take the double slit experiment. According to quantum mechanics, the wave function of the electron is a superposition of the electron going through one slit and the other slit simultaneously. Using this wave function, you can calculate the probability of where the electron is likely to be. And then when you detect it at the screen, the electron pops up at one point at random that was in that distribution. We say that its wave function collapses instantaneously at the moment of measurement. You can't say that the electron was there before you measured it, and you can't even say that the electron must have gone through one slit or the other. Compare that with the picture provided by the bouncing droplets. In this case, the pilot wave goes through both slits, but the droplet only goes through one. The droplet is pushed around by its interaction with the wave so that the resulting statistical distribution is the same. The droplet never exists in two places at once, and there's no randomness. If there is any uncertainty, it's just due to our ignorance of what's going on. It's not that it doesn't exist. So pilot wave dynamics can produce many of the same results as quantum mechanics. Does this mean that this is really what quantum particles are doing? No. But I think it'll at least suggest that this is possible. These are possible dynamics that could lead to the statistics which are captured in the quantum mechanical theory. And what's appealing about this is it gives you a clear idea of what's going on. You don't have to abandon the idea that the universe is deterministic, and you get particles with definite position and momenta. I think it's great that we have two competing theories for the same experiments, and they both ask you to accept odd things, just different odd things. And it comes down to what you're comfortable with, really, whether you prefer the Copenhagen interpretation of standard quantum mechanics or a pilot wave theory. Let me know what you think in the comments. Do you like the pilot waves? I mean, it's definitely a very appealing picture. Whether or not it corresponds to reality, that remains to be seen.
So, when I first saw that video, I honestly, that's bonkers. Like I looked at quantum mechanics a while ago in university, and this wasn't out there at the time. But I don't know. I find it astounding. He mentions in the video like there's these two competing theories. There's way more than that. You're gonna see. But he was just focusing on pilot wave versus Copenhagen. The spoiler alert out there that when we get to the Copenhagen interpretation, it's really just none of this matters. Like don't worry about whether it's a real particle. Don't worry about any of it. Just focus on the math. It gives us good results. That's the Copenhagen interpretation, which. Yeah, I don't know. It's not for me, that's for sure. But let's keep going here. So I'm going to set up the video for many paths. Just bear with me a sec.
Now, I have thought about and taught the double slit experiment hundreds of times without fully realizing this implication. In the double slit experiment, I feel like the mental thing that I'm doing in my head is like, okay, well, the beam is not perfectly straight, and of course it's going to intersect both of those slits, because they're really close together, But then I heard this story about a professor teaching the double slit experiment, and it makes everything so clear. So the professor starts by explaining the setup. Electrons are fired one at a time through two slits to be detected at a screen. Now, because you can't say for certain which slit the particle went through, quantum mechanics tells us it must go through both at the same time. So to get the probability of finding a particle somewhere on the screen, you simply add up the amplitude of the wave going through one slit with the amplitude of the wave going through the other slit and square it. But that's when a student raised his hand. What if you add a third slit? Well, you just add up the amplitudes of the waves going through each of the three slits, and you can work out the probability. The professor wanted to continue, but then the student interjected again. What if you add a fourth slit and a fifth? The professor, who is now clearly losing his patience, replies, "I think it's clear to the whole class that you just add up the amplitudes from all the slits. It's the same for 6, 7, etc." But now the bold student pressed his advantage. What if I make it infinite slits? So that the screen disappears. And then I add a second screen with infinite slits, and a third, and a fourth. The student's point was clear. Even when we're not doing a double slit experiment, when it's just light or particles traveling through empty space, they must be exploring all possible paths. Because this is exactly how the math would work if you had infinite screens, each with infinite slits. You have to add up the amplitude from each slit. That's just the way it works. According to the story, the student was Richard Feynman. And while the story is made up, the logic is flawless.
Because if you believe in a double slit experiment, that you can't tell which of the two slits the particle went through, then you have to consider the possibility that it goes through both. By that same logic, anytime any particle goes from place 1 to place 2, you have to consider all the possible paths it could take to get there, including ones that go faster than the speed of light, including ones that go back in time, and including ones that go to the sun and back.
I feel like it can't go to the sun and back. You have to restrict it to be local, right?
So the math doesn't do that. I mean, you could see that just in the double slit experiment.
So I would describe that question asked by that student as one where I'd like to go back in time and tap myself on the shoulder when I'm in a lecture hearing about this, and think, why didn't I think of asking that, right? Same as when I was in chemistry class and the teacher was saying that electrons are attracted to the protons, and that's the model of the atom. You know, why didn't I ask why don't all those positive protons repel, right, from each other? And of course, the answer is they're held together by this other physical force in the universe called the strong nuclear force. It's stronger than the electrostatic repulsion force. So really good question, and it led to this, idea of the particles having to sort of search out all possible paths, right? So I'm going to go back to the beginning, and it's going to lead to it's going to go over the ultraviolet catastrophe for you, and it's going to link to even a reason for Bohr's shells, like the organization of the shells and the 288 business in atoms. So the link back is that not only do little particles of photons and electrons and any other little particle that we can make behave quantum mechanically, even buckyballs, which is like 60 carbon atoms, can be observed to do this. So basically the idea is that we don't notice it in everyday life because the effect is very, very, very small and subtle, but it actually is a real thing, right? So basically many paths for all objects. So let me get the rest set up here. I have to turn my mic off so you can hear the computer better. So one sec.
As a 42-year-old who's spent most of my life studying physics, I must admit that I had a big misconception. I believed that every object has one single trajectory through space, one single path. But in this video, I will prove to you that this is not the case. Everything is actually exploring all possible paths all at once. So let's start with a simple thought experiment. Say you're at a beach when all of a sudden you see your friend struggling out in the water. You want to go help him as quickly as possible, so which path should you take to get there? The shortest path is a straight line. so you could head directly towards him. But you can run faster than you can swim, and this path requires more swimming. So alternatively, you could run down the beach to minimize the distance through the water. But now the total distance is longer than it needs to be. So the optimal path, it turns out, is somewhere in between. To be precise, it depends on the speeds at which you can run and swim. Now, you might recognize this mathematical relationship because it is the exact same law that governs light passing from one medium into another. So light also takes the fastest path from point A to point B. What's weird about this is that as humans, we can see where we want to go and then figure out the fastest route. But light? I mean, how does light know how to travel to minimize its journey time? Now, here is where my misconception comes in.
I shine a laser beam. The light just goes in one direction. I throw a ball. The ball just goes in one direction, you know?
I would have answered, there is nothing strange about this. Light sets off from point A in some direction, and then a little while later, it encounters a new medium. And due to local interactions with that medium, it changes direction, ending up at point B. If you later find that of all the possible paths, light took the shortest time to get from A to B, I wouldn't think it was optimizing for anything. I would just think that's what happens when light obeys local rules. But now I will prove to you that light doesn't set out in only one direction. Instead, it really does explore all possible paths. And the same is true for electrons and protons, all quantum particles. So the fact that we see things on single, well-defined trajectories is, in a way, the most convincing illusion nature has ever devised. And the way it works all comes down to a quantity known as the action. In a previous video, we showed how an obscure scientist, Maupertuis, made an ad hoc proposal that there should be a quantity called action, which he defined as mass times velocity times distance. And he claimed that everything always follows the path that minimizes the action. Hamilton later showed that this action is equivalent to the integral over time of kinetic energy minus potential energy. Action was useful and an alternative way of solving physics problems, especially when Newton's laws get too cumbersome. But then, around the turn of the 20th century, action showed up at the heart of a scientific revolution, the birth of quantum mechanics. It all started with electric lighting in Germany.
Think about what it's like in the 1890s, right? Electricity being more widely available, at least in urban centers, and things like, light bulbs. They were new. They were literally the hot new thing.
Germany wanted to replace all their gas streetlights with electric light bulbs. So an important question was, how do you maximize the visible light given off by a hot filament? Scientists at a German research institute, the PTR, studied how much light different materials emitted as a function of temperature. At low temperatures, each material gave off its own characteristic spectrum, mostly in the infrared. But above about 500 degrees Celsius, all materials started to glow in the same way, with an almost identical distribution of light. The hotter the object, the more energy was emitted at every wavelength, and the peak of the distribution shifted to the left.
But they still didn't understand how it worked theoretically. So that was sort of the next step, right? Because if you can understand how it works theoretically, then you can use that theory to potentially design new products.
They started by imagining the simplest object possible, one that would absorb all light that falls onto it and perfectly emit radiation based on its temperature. They came up with a hole in a metal cube. This hole is a perfect black body because any light that shines onto it will go straight in, bounce around inside, and eventually be absorbed. But this also makes it a perfect emitter. Any radiation inside the cube can escape through the hole unimpeded. Theorists reasoned that electrons in the walls of the cube would wiggle around, emitting electromagnetic waves. These waves would then bounce off the other walls. When you have two waves of the same frequency, where one travels to the right and the other to the left, they can interfere in such a way that they create places where there's no wave amplitude, those are nodes, and places where there's maximum wave amplitude, the antinodes. Waves like this are called standing waves because they don't really move left or right. And inside a cavity, given enough time and reflections, it is only these standing waves that survive. All the other ones just cancel out. So a sort of order emerges from the chaos. In 2 dimensions, standing waves look something like this. For shorter wavelengths or higher frequencies, you can fit more and more different vibrational modes inside this cube. So that in 3 dimensions, the total number of modes is proportional to frequency cubed, or 1 over lambda cubed. The expectation was there would be more and more waves inside the cube the shorter the wavelength. This led directly to the Rayleigh-Jeans law. At longer wavelengths, it matched the experimental data pretty well. But at shorter wavelengths, the theory diverged from experiment. In fact, it predicted that at the shortest wavelengths, an infinite amount of energy would be emitted. This, for obvious reasons, became known as the ultraviolet catastrophe. The person to solve this problem was Max Planck.
But Planck almost didn't make it into studying physics. Because when he was 16 years old, he went up to his professor and asked him, well, maybe I could do a career in physics. To which his professor responded that he'd better find another field to do research in, because physics was essentially a complete science. You know, there was just a few tiny little problems that they had to clean up. But besides that, it was over.
But Planck didn't listen. By 1897, he was a professor himself, and for the next 3 years, he struggled to find a theoretical explanation for blackbody radiation. He tried approach after approach, but no matter what he tried, nothing worked. He said, "I was ready to sacrifice every one of my previous convictions about physical laws." Then, in a quote, act of desperation, he did something no one had thought to try. According to classical physics, the energy of an electromagnetic wave depends only on its amplitude, not its wavelength or frequency. And it could take any arbitrary value. So any atom could emit any wavelength of light with an arbitrarily small amount of energy. But Planck tried restricting the energy so that it could only come in multiples of a smallest amount, a quantum. And he made the energy of one quantum directly proportional to its frequency, E equals hf, where h is just a constant. Think about what this does to the radiation coming from the black body. At a given temperature, the atoms in the cavity have a range of energies. Some have a little bit, a few have a lot, and most have their energy somewhere in between. For long wavelength, low frequency radiation, the energy hf of one quantum is small, so all of the atoms have enough energy to emit this wavelength, and the spectrum matches the Rayleigh-Jeans prediction very well. But at shorter wavelengths, higher frequencies, the energy of a quantum increases. And now, not all of the atoms have enough energy to emit that wavelength. This is why experiment diverges from the classical prediction. The spectrum peaks and then starts to fall, because fewer and fewer atoms have enough energy to emit one quantum of that radiation. And there comes a point when none of the atoms have enough energy to emit one quantum. So here, the spectrum must drop to zero. With this approach, Planck got a new formula for the radiation spectrum. Now, all that was left for him to do was to tune the parameter h, and when he did this just right, he got his formula to match up perfectly with experiment.
But he was sort of troubled by his own formula, because to him it was just a mathematical trick. He had no clue why it worked. It was purely formal. And most importantly, he had no clue what this h represented. I mean, he had introduced a new physical constant without any reason.
He wrote, "A theoretical interpretation had to be found at any cost, no matter how high." So from that moment on, he dedicated himself to finding one. He later reflected that after some weeks of the most strenuous work of my life, light came into the darkness, and a new, undreamed of perspective opened up before me.
He introduces what we now call Planck's constant, and it has the units of action. Planck's constant h is a quantum of action.
Planck later proposed that anytime any change happened in nature, it would be some whole multiple of this quantum of action.
So it's kind of spooky. This breakthrough that starts the ball rolling toward quantum theory brings action in, not energy and not force, action. Gives you a hint.
At first, the quantum of action got little attention. That is, until a 26-year-old patent clerk came on the scene. In 1905, Albert Einstein claimed that Planck's theory wasn't just a mathematical trick. It was telling us that light actually comes in discrete packets, or photons, each with an energy hf. Einstein used this insight to explain the photoelectric effect, how light can eject electrons from metal, but only when the frequency is high enough. If the frequency is too low, no electrons will be emitted, regardless of the intensity. The idea of quantization spread. 8 years later, Niels Bohr was trying to understand how an atom is stable if it has a positive charge in the center and negative electrons whizzing around it. Why don't they just spiral into the nucleus, radiating their energy as they go?
And what he wants to do is, he says there's something fishy about something being discrete. That seems to be the new, ambiguous, weirdo lesson of the new quantum of action.
Bohr realizes that as the electron goes around the nucleus, it has an angular momentum. Mass times velocity times radius. So angular momentum has the same units as action.
And so what he decides to do is discretize the orbital angular momentum for no good reason. He says, let me slap that on and say angular momentum of the electron can only be in 1 unit, 2 units, 3 units of the same quantity h. And because it's talking about motion in a circle, the factors 2 pi come in, so it's really nh over 2 pi, what we now call nh bar.
This comes out of nowhere. There seems like absolutely no good reason why angular momentum should be quantized. But by doing it, Bohr finds the correct energy levels of the hydrogen atom. When an electron jumps from a higher orbit to a lower one, the energy difference is given off as a photon of a particular color of light, exactly reproducing the hydrogen spectrum.
And that was a pretty startling thing to have fall out. I think that really was compelling. And take some quantity with units of action and apply some, again, kind of ad hoc just discretization or quantization to it.
Now, although it worked spectacularly well, no one could make sense of it. That is, until 11 years later. For his PhD, Louis de Broglie was contemplating the recent discoveries in physics, and his big insight was that if light could be both a wave and a particle, then maybe matter particles could also be waves. He proposed that everything, electrons, basketballs, people, absolutely everything has a wavelength. And he defined this wavelength analogously to light, as Planck's constant divided by the particle's momentum, or mass times velocity. Now, if an electron is a wave, the only way it could stay bound to a nucleus in an atom is if it exists as a standing wave. That requires that a whole number of wavelengths fit around the circumference of the orbit. You could have 1 wavelength, or 2 wavelengths, or 3, and so on. So the circumference 2 pi r must be equal to some multiple n times the wavelength. We can sub in de Broglie's expression for the wavelength to get that 2 pi r equals nh over mv. But we can rearrange this to get that mvr, the angular momentum, is equal to nh over 2 pi. That is precisely Bohr's quantized angular momentum condition. But now we have a good physical reason why it's quantized, because electrons are waves and they must exist as standing waves to be bound in atoms.
Because they want to have constructive interference of a stable orbit back. That's pretty good. You get a dissertation out of that. That's pretty good.
It is this wave nature of quantum objects that means they no longer have a single path through space. Instead, they must explore all possible paths. Now, I have
man, I hope you're as flabbergasted by that video as I am, or as I was when I first saw it. Like it's just it encompasses so much of what we've done. Such an awesome, pulls it all together kind of thing. Historical journey of how Bohr thought of his thing, and then how de Broglie's wavelength, gave a reason for it, and the H, Planck's constant, being a quantum unit of action, just like the charge on electrons, a quantum unit of charge, and I don't know, crazy. I left this video for you because I think it's copyright heavy. You can look through it. It's not as good as the other stuff we've done though. So yeah, pilot wave, pretty good. The many world interpretation, I just don't understand how anybody puts any stock in this one, but every time a decision is made, or the universe branches off and there's an infinite number of universes being created at all times, it just doesn't make any sense to me. But there's been good, correct theories that have been ignored by lesser minds as well, so I could be in that boat. The transactional interpretation, I've heard of. I didn't see it in university, I don't think, but it was a little while ago. This takes advantage of the often ignored negative time in the equations, and so negative time is often just ignored, right? Like think of your quadratic equation solutions for when a projectile motion ball lands. There's often these two answers of that lands 3 seconds later or 1 second before it was launched. We're just obviously we intuitively ignore that negative number. But in quantum mechanics, it could mean objects moving backwards in time, and it gives a possible explanation of quantum entanglement, because basically the antiparticles themselves are thought of as regular particles that are traveling backwards in time, so that that there's some merit here in terms of interpreting things. So yeah, all the leading interpretation of all of this weirdness though is the Copenhagen interpretation, which, like I said, it basically just says, like just ignore all that. Everything just exists in a so-called superposition of states, which doesn't really mean anything, but just they all exist, sort of, kind of, and well, they say they all exist. When an observation is made, then all of those possible states collapse, and you observe the one, right? So it just agrees with experiments, doesn't really tell you anything, but all of the interpretations agree and lead to these same mathematical equations, right? So that's the, if you go in and study quantum mechanics, this is the main one you're going to see, because it's just basically, let's just focus on the math. So there's you've probably heard of the Schrodinger's cat, the thought experiment, and so the Copenhagen interpretation, particles are in these superposition of states. And so Schrodinger, listened to that and said, well, okay, that's ridiculous. And he said, what if we had a cat that was in a box? Like the whole point of the Schrodinger's cat is either to, I'm not sure if it's to discredit the idea of the Copenhagen interpretation, or if it's to just to, display to all of the scientists in the world how bizarre it is, okay? But if they're in superposition of states, it means that until observed, they're not really in either state. They're in some kind of indeterministic limbo, like they're in both states, right? So you have this cat in the box, and it's in there. So the illustrate the paradoxical result, or the idea of the Copenhagen interpretation, that there is a Geiger counter in there with a hammer and a small amount of radioactive material and a vial of some toxic substance. So if the atom radioactively decays, then the hammer will crash and it'll release the substance and it'll kill the cat. Poor cat, right? So since, according to quantum mechanics, darn it, lock that thing in place. There we go. Since, according to quantum mechanics, the atoms exist in a superposition between decayed and not decayed, or killed and not killed, until we open the box, the cat is actually in a superposition of being alive and dead. Until we see it, there's no actual fact of matter there, right? And so, yeah, so it says, so the person says, so you're saying the cat's neither dead nor alive, but in some sort of state between the two? And the scientist is like, yeah, that's the idea, basically, more or less. It's complicated. So Schrodinger figured out how to use the power of quantum mechanics to make zombie cats. The person's like, no, I don't think so. And there's the zombie cat wanting brains. Obviously, it's a silly cartoon joke, but I mean, it's a good summary. I thought it was a funny summary of Schrodinger's cat. So the point is that cats, of course, don't really behave like this, but subatomic particles really do. Like the experiments don't, the experiments show that this is how quantum particles really do behave, which is bizarre, right? So then funny things like Schrodinger wanted dead and alive rather than dead or alive. A joke here about Heisenberg and Schrodinger. So Heisenberg you'll learn more about soon, but Schrodinger traveling in a car and pulled over by a police officer. The officer asks, you know how fast you're going? And Heisenberg asks, no, but I know exactly where I am. So that joke will make more sense tomorrow, that part of it. And in the next lesson, whenever you watch it, this arouses the officer's suspicion. So he asks to check their trunk. He looks inside and he asks, do you know there's a dead cat in your trunk? And Schrodinger replies, well, I do now. But, you know, implying the cat was in a superposition state, so he didn't know whether it was dead or alive, right? And now that the police officer observed the cat, right? So that's a key part of the Copenhagen interpretations, that observations are a key part of the math of it, which is bizarre. Like what qualifies as an observation? It's kind of bizarre. And then we get to the point of saying, okay, well, you know, this stuff seems kind of bizarre. You know, is there any meaning to this? Does it matter? Like, you know, are there any uses of it? And it turns out, yeah, there's a bunch. So here we go.
We really do know what's going on at the subatomic level. We have a complete and accurate mathematical description of what happens.
That mathematical description is something everyone agrees on. It allows us to make incredibly accurate predictions, and that's very useful.
Something that people didn't anticipate is that if you have a weird version of reality, then you can make that weird version of reality do some work for you.
Do some work for you? That's weird.
How can quantum work for us if we don't even know what's going on?
We know what's happening. We just don't know why.
If we can't measure a quantum object without disturbing it, what can we possibly make?
Plenty.
Quantum physics is invading everyday life, even if we're not aware of it. And so as the world becomes increasingly more technology-oriented, we're just going to see a world that is increasingly quantum physics-oriented.
Many technologies take advantage of the wave behavior of electrons. One of them is the electron microscope. An electron with a large momentum has a wavelength much smaller than visible light, so scientists use electron microscopes to resolve objects down to the level of individual atoms. We can look at strands of DNA, examine viruses, and design nanotechnologies. The particle nature of light is at the heart of a range of everyday technologies. Traffic lights, solar panels, barcode scanners, and remote controls are all devices that incorporate quantum effects related to photons.
Inside modern devices for information processing, like CD players, cellular phone, computers, there are, at the brain itself, there's an element called a transistor. And the transistor would not work today if we would not have the laws of quantum mechanics.
We can control the flow of electricity. We can amplify it, we can turn it off, we can turn it on. Our ability to turn things on and off, control the flow, gave us logic gates. Those logic gates, when we were able to replicate them on a mass scale through commercialization of that discovery, led to integrated circuits led to computers, computers led to the information age and the internet.
If you do not think quantum mechanics is important and you do not like quantum mechanics, you can choose to live your life without it. Please get rid of your cell phone, your iPod, your computer, all electronic equipment, and then you can live your life without quantum mechanics.
I had no idea my phone was quantum.
No one knew the range of technologies possible when the theories were first presented 100 years ago. But our knowledge developed over decades.
Quantum mechanics has revolutionized the way we live our life. The development of the technology and applications enables more science to be done. As more science is done, more technology and more applications are developed.
At the Institute for Quantum Computing in Waterloo, Ontario, researchers are developing a range of new quantum technologies. Quantum cryptography takes advantage of the concept of measurement disturbance. It's the basis of ultra-secure secret codes that are starting to be used by banks and governments to safeguard highly sensitive information.
In quantum physics, when you make a measurement, it doesn't tell you everything about the system you're looking at. And further, just by looking at the system, you change it. In cryptography, we can use this to detect eavesdroppers. So not only can an eavesdropper not get all the information about a system, but will inevitably change the signal and can be detected. So it's quite clever, actually.
Researchers are also using quantum physics to build a new breed of ultra-powerful computers.
So the idea of a quantum computer is, suppose you built a computer out of individual atoms or other very small objects that were behaving quantum mechanically. Then instead of just having one number in its memory and doing computations on that one number to get an answer, it could have, in some sense, many numbers at the same time and do computations on all of them. And so consequently could solve some problems much faster than any regular computer.
In the case of quantum computing and quantum cryptography, we go much deeper in the quantum world, much kind of places where we don't only put our big toe in the ocean of the quantum world, but really go and swim in it.
And what's really exciting is that we can't even imagine the kinds of discoveries that our future physicists are going to make. But what we know is that they're going to absolutely transform society.
So there's a really good example of, if you're looking, you hear about scientists and physicists, researching things that are really obscure, really, specific to their field and so on. When are we ever going to use that kind of thing? Be like, yeah, you don't know what things are going to lead to. So just let people do cool stuff, really, right? Another very strange quantum effect we talked about in the videos here and that was this measurement disturbance idea. Right, so I didn't talk about it as much until just now, whatever. But if you look to see which slit electrons go through, then the the double slit quantum mechanical interference pattern disappears. And so one more here, and then we're done.
Remember Thomas Young's double slit experiment?
Yeah, it showed that light produces an interference pattern.
Right.
So light is a wave.
Right again. But what happens if we turn down the intensity of the light?
Like we did with the electrons.
Exactly.
At Brown University in Providence, Rhode Island, researchers are performing the double slit experiment with light. They have very sensitive detectors that can detect light even when it's extremely faint. When the intensity of the beam is turned down, we see that light hits the screen as individual, localized particles. This provides strong evidence that light is made of tiny bundles of energy called photons. The energy of a photon is equal to the product of Planck's constant and the photon's frequency. The higher the frequency of a photon, the more energy it has. After many photons hit, the same interference pattern appears on the screen. So like electrons, light exhibits wave-particle duality.
When we study light, it can be a wave, completely a wave. And then we change the experiment and it looks entirely like a particle.
So now we have light and electrons on the wave-particle duality list.
That should do it.
Not quite. Wave-particle duality isn't limited to light and electrons. Wave-particle duality is one of the defining features of all quantum objects.
Like electrons and light, protons, neutrons, and atoms behave like particles in some situations and like waves in others. Some researchers have even observed wave behavior in molecules. In 1999, researchers in Vienna, Austria observed an interference pattern for molecules made of 60 carbon atoms. Since then, they've continued to increase the size of the molecules in their experiments.
The first question is how big, how complex can such a quantum object be before quantum mechanics breaks down?
To me, this is just a technological question. We are now learning to see quantum effects for larger and larger objects, and I'm convinced that someday we will actually see them on an everyday scale.
No one knows where it'll break down or if it will break down,
at any point, and nobody can delineate a sharp boundary between the classical and the quantum worlds. This is a major open question.
So the electrons hit the screen one at a time like particles.
Right.
But when both slits are open, we get an interference pattern, like waves.
Even when we fire them one at a time.
Correct again.
Doesn't that strike you as a little weird? I mean, how can something that hits like a particle produce an interference pattern?
Does each electron go through both slits, like a water wave does?
All good questions.
I got it. If we want to know what the electrons are doing, why don't we just look at them?
Yeah.
Someone already thought of that.
Researchers in Tübingen in Germany placed measuring devices next to the slits. When they fired electrons at the slits, half of them went through the left slit and half went through the right.
See? Told you. Problem solved.
Not so fast.
When the researchers looked at the screen, something had changed. The interference pattern was gone, replaced by a completely random distribution.
Measuring a system disturbs it, and so even though there's interference there when you're not looking at it, as soon as you look at which slit the electron has come through, it collapses into one of those two possibilities and looks like it's acting like a particle.
Many other experiments have also shown that measuring a quantum object disturbs it. It's as if the quantum world is resisting our attempts to unlock its mysteries.
In classical physics, when you measure something, that object stays the same. We're constantly being measured, and I don't change just because the light is shining on me right now. But in quantum physics, if you shine light on an object, you disturb it inevitably. So in particular, when we try to measure something in quantum physics, then what we're trying to measure will be gone.
Consider, for example, that you're trying to measure the position of a basketball. If you can use your eyes, the basketball's flying across the room, you can see where it is, and you don't disturb it. But now pretend you were blind, and all you could do was throw, say you had a pile of baseballs there. You're throwing the baseballs at the basketball, some of them will hit, they'll come back, they'll tell you where it was, but every time they hit, they kick it a little bit, and that ruins the information. And in quantum mechanics, you don't have the option of doing anything other than disturbing the system when you measure it.
So we can't measure electrons or other quantum objects without disturbing them.
That's right.
You still haven't answered my question. What were the electrons actually doing between the source and the screen?
It depends on your interpretation, so we don't totally.
Square one there, and that goes into the interpretations business. So yeah, that is all for now. So I hope I've done my job correctly, and you are now confused about quantum mechanics, because that means you're on your way to understanding it, apparently. So I don't necessarily have to do all those, but I mean a bunch. Okay, all right. That's all for now. It's a long one.